Alex Lawrence Barkley here at AutoSens Detroit. I'm here with Wade Appelman from SensL. Wade, welcome to AutoSens.
Hi, Alex.
This is your second time with us, isn't it?
Yeah, we were an exhibitor also in Belgium. We're a fabless semiconductor company, so when you think solid-state LiDAR, you have to think of the components that make up a solid-state LiDAR system. So we're not building the complete LiDAR box, we're building the sensor that enables solid-state LiDAR.
Right, so we've got a laser here. In this little demonstrator, we've got a laser on the left on this side, and we've got a detector on this side, and inside that there's a very, very small chip, which is not a conventional chip, is it?
Right. We call these devices silicon photo-multipliers, or SiPMs. And they compete with other technologies that people may be familiar with, such as pin diodes or avalanche photodiodes. But the real advantage of an SiPM is that it can go much further distance. So it can see a target that in some cases is maybe 200 meters away and is low reflectivity. You have to be able to see those return photons, so being able to see a single photon coming back is a critical advantage, and that's what silicon photomultipliers do, is if you optimize your system with the correct optics, the correct wavelength of the laser, run that laser at the correct speed to eliminate ambient light, you can get really good results using a silicon photomultiplier, and that's what we've been demonstrating here at this show.
And so just to quickly talk through the types of chips we've got here, most people in their camera phones are typically using maybe a 4 or 5 millimeter chip to get really high resolution, thousands and thousands of pixels, and megapixels of course, but these are different. These are looking like the sorts of chips that you find in medical devices.
Well, we do, silicon photomultipliers initially were used in medical imaging, specifically nuclear medicine, and we've been doing that for a number of years and produce these in very, very high volume. The LiDAR market is a natural extension for us to move into, but again, these are not imagers. If you look at a device like this is not an 8x8 imager. What this is it's using each individual pixel to count photons, and then we're able to create a scene by counting the photons coming back and running it through the processing algorithm.
So this is a 64 pixel sensor.
Yeah, exactly. But customers have typically, what we're showing now today in this show is for LiDAR, you want a very, very small pixel. Okay, so this is a very large pixel area. This new one here is a 1x16 SiPM array of just 1 millimeter detectors. So when mounted in a scanning LiDAR system, it's able to give a very good field of view of 100 degrees in one direction by upwards to 25 to 40 degrees in the other. So we're getting really good performance at long distance.
SiPM, can you just explain how that makes a cost difference to what LiDAR is now and what it can become in the future as a solid-state solution?
So the goal of solid-state LiDAR is to bring the cost down to sub $250 to the OEM. So that's a bill of material cost of $50 to $60 ultimately. We're not there yet today as an industry, but we're striving for that. But what you want to be able to do is use commercial off-the-shelf products, so that's why lasers at 905 nanometers are very popular, because they're able to be produced in high volume at low cost. Silicon photomultipliers in the same way also can be produced in very high volume at very low cost. Beam steering is yet another very important element of cost of a LiDAR, but once all three of those major components come down in price, that's what's going to enable you to get to those prices, and silicon photomultipliers are key enabling technology.
Wade, thank you very much for joining us, and it's great to see you here and great to see SensL progressing with good conversations. Lots of different companies around coming to see you. I noticed your stand's been really busy as well.
Yeah, it has been.
So we'll look forward to seeing you in Brussels.
All right, sounds good. Okay. Thanks.